Okay, now we're going to talk about the Black Litterman model, and the goal here is exactly the same as the single index model. That is to find the optimal risky portfolio, or what we'll call the model portfolio. So we need the same things. We need to have expected returns, and we need to have a covariance matrix. And Fisher Black and Robert Litterman at Goldman Sachs developed this model, and they developed it because if you use the Markowitz approach, like we talked about before with the historical data, you come up with bogus numbers, and it doesn't make any sense. It doesn't pass the smell test, so people just won't use it. So they wanted to come up with something that would actually work, that you could implement for real. So this is still used by a lot of people particularly in the more quantitative shops. Alright, step number one is estimate the covariance matrix from historical data. So what they said, covariance matrix, what they said is we're going to take historical covariance matrix to be right, to be a good predictor of the future. And it turns out the the inputs, the model, the Markowitz setup is most sensitive, first of all, to expected returns, and then to covariance, and then to variances, and then to covariances. So they said, Black Litterman said, let's just take the covariance matrix from historical data and keep that as it is. So in our example, we're going to say there are bonds and there are stocks, and that's it. And we're going to say, so this is bonds, and the variance of bonds is 0.0064, and the covariance between stocks and bonds is 0.00408. Stocks over here. So this covariance of stocks and bonds is the same as bonds with stock, and 0.0289. Now you're free to, and Litterman did make some changes to this after Fisher Black had passed away, but you're free to estimate the covariance matrix like we did with the single index model if you think that's a superior covariance matrix. But for now, we're just keeping it with historical because that's what they did. Step number two is determine a baseline forecast. And this is where it gets a little messy, but hopefully you can see how this makes sense. Alright, so their baseline forecast goes something like the following. My expected return on bonds, and this will work the same way for stocks, my expected return on bonds is equal to the beta for bonds times the expected return on the market. And I'm going to drop the e's here just to make it easier, so I'm going to write this. So you know I mean expected here. The return on bonds is equal to the beta of the bonds times the return on the market, which is in this case the market risk premium. So anyway, we're assuming alpha is 0 because if markets are efficient and if the cap M is true, then alpha should be equal to 0. So what's this return on the market? Return on the market, according to cap M, if you go back to your notes in 8000, I don't know if you did this or not, is equal to A times the variance of the return on the market, where A is the level of risk aversion, and we're going to just assume for our class that A is equal to 3 because that's a pretty good estimate. And then I need the variance of the market. Alright, so I have the variance of the market from this data right here, but you just don't see it. So let me do that up here. The variance, I'll write it like this, the variance of the market is equal to the weight in stocks squared times the variance of stocks plus the weight in bonds times the variance of the bonds plus 2 times the weight of stock, weight of bonds, covariance between stock and bonds. So what Black and Litterman do is they say, let's look out and see the total value of stocks in the market. And there are only two things in our simple world. There's stocks and their bonds. Well, 75% of the tradable securities are stocks and 25% are bonds. So all I have to do to get the return on the market, or to get the variance of the market, is substitute in. So variance of the market is equal to 0.75 squared times, for stocks it's 0.0289 plus 0.25 squared times the variance for bonds plus 2 times the weights, 25 and 75, times the covariance, 0.0408, and that equals 0.018186. So, go back over here, my return on the market is equal to 3 times this, which is equal to somewhere around, rounding off here, 5.46%. Alright, so now I have this number. How do I come up with the rest of this? Well, I got to do a little bit of math to do this. Sorry about that. So let me pull this up just a little bit. The return on bonds is equal to the beta. Well, before I do this, what's beta equal to? The beta of the bonds is equal to the covariance of the return on bonds and the return on the market over the variance of the market. So that's just the definition of covariance. The return on bonds is equal to covariance of the return on bonds with the return on the market over the variance of the return on the market times the return on the market, which is equal to A times the variance of the return on the market. This is equal to A times the covariance, return on bonds, return on the market. We know A is equal to 3, but what about this term right here? Well, the covariance of return on the bonds with return on the market is equal to, let's substitute in, what is the market equal to? The market is 25% bonds plus 75% stocks. So that's going to be 0.25. When I'm doing covariance, I can take the constant terms out. This is constant, this is constant. So what I'm doing, I'm going to say, look at this term and then that one. So 0.25 comes out, and that's times covariance of return on bonds with return on bonds plus 0.75 times the covariance return on bonds with return on stock. Remember, this is just the variance of the return on bonds, so that's 0.25 times 0.0064 plus 0.75 times 0.00408. Hang on just a second. Okay, so now this is equal to 0.00466. So the return on bonds is equal to 3 times 0.0466, and rounding that off, it's equal to 1.40%. There's a little rounding there, but good enough. If I do the same thing, return on stock, it comes out to be 6.81%, and you can check that if you want to. So this is what we now have. We need to have the covariance matrix as an input to the model. So bonds, stock, that's 0.0064, 0.00408, and 0.0289, and then the return on the bonds is equal to 0.140. Return on the stock is equal to what I put up there, 0.0681. And now I can plug this. So I have the covariance here, returns here, plug those into the optimizer, into a real nasty equation, and what comes out are the weight of stocks and the weight of bonds. And in this case, I know it's going to come out to be 75% and 25%. So let me kind of review here. What we've done is we said we have, I didn't mean to do that. Hang on, let me see if I can fix it. Okay, so let's go from here. Let's review. So we know in order to find the optimal risky portfolio or the model portfolio, we take a covariance matrix and we take the expected returns, plug it into the nasty into nasty equation, an optimizer in a spreadsheet, and it comes out with the weights, and this is what we're looking for. So what Black and Litterman say to do is let's start with the weights that we observe. So I know that the market weights are this, and I know the covariance matrix is this. So given that, what returns had to go into the optimizer to come up with this? So in other words, what returns right here were needed to combine with the covariance matrix to put into the optimizer to come out with the weights? That's what we found. That's what they call their baseline forecast, and it's 1.4% for bonds and 6.81% for stocks. And this is the cool part of the Black-Litterman model. It says we can put in step 3. We want to put in private views. So this is a simple 2-asset example, but you imagine you have 100 stocks or 1,000 stocks, or whatever. I can't be an expert in everything. So I'm a bond expert. I know more than anybody else about the bond market. I don't know nothing about stocks. Nothing about stocks. So if you don't know anything about stocks any more than anybody else, what do you do? So I take the market view. How do I know what the market view is? Well, I know that everybody else is, well, not everybody, but on average, average people have in their model portfolio 75% stock and 25% bonds. So the people on average have the historical covariance matrix. So if I back those numbers out, that means the average portfolio manager must estimate a 1.4% return for bonds and 6.81% return for stocks. So I'm not a bond expert. I'll take the market view of 6.81%. I am a bond expert, and I don't believe 1.4%. I think it's 2%. So what I do in my optimizer now is I get rid of this and I put in for bonds 2%, and then I come up with new weights. And I don't have those weights handy, but you can imagine it's going to be, since you upped your allocation to bonds, the 25% number here is going to go up, and the stock number is going to go down. And the last thing here is, or two last things here, your private views are how sure, or what's your confidence level. And we're not going to get into the math of this because this math gets really messy. But basically you can say how confident are you that your private views are correct, and the last thing you do is you blend those views together. So blend your private views with market. And this is going to be your final weights. We'll go through an example in class, but that I want you to kind of get the intuition behind this. So let's see if I can scroll back up and just leave you last. No, I can't do it. So let me do it this way. In review, I use historical covariance matrix. Two, I determine my baseline forecast, and my assumptions here that the market uses historical covariance matrix and the market uses the CAPM to come up with their returns. And then I put in my private views, and then I say how confident am I in those private views. And in step 5 I blend market with private. And that's it.